session is Dr. Durgesh Rai, who is currently a professor in the Department of Civil Engineering at IIT Kanpur. Sir has published over 150 peer-reviewed papers in journals and conferences in the area of structural and earthquake engineering. In his previous session, Sir has explained to us how structural behavior of elements work via videos of the experiments that can be inferred from experiments and their conclusion. It was a wonderful session, sir, and I'm sure this one would be even better. It is really an honor to invite you again to speak on another topic named earthquake performance of confined masonry structures and Indian codal provisions. Recently in 2021, Sir has received the John B. Scalzi Research Award in the same field by the Masonry Society USA. We have already heard about Sir's graduation, professional experience and achievements. So without ado, I would request Dr. Durgesh Rai to start this session and bless us from his ocean of knowledge and experience. Over to you, Durgesh, sir. Sir, you are muted right now, Durgesh, sir.
Okay, so that's fine. Can you see my screens now?
Yes, sir.
Okay, good. Thank you. Good afternoon to participants, and it is really a pleasure to again connect with you, and now with a different topic. As Mr. Patel mentioned that we'll this hour and a half we will talk about the confined masonry, and this is a alternative building typology for earthquake resistance. And what we will see that, this earthquake resistance is not a new phenomena. Earthquakes have been as old as the earth is, and human civilization has always came up with the ideas and schemes and techniques, to protect it from the devastating earthquakes, especially on dwellings and structures. So, and the problem is still the same as it was centuries earlier. So if you visit the areas which have been more earthquake prone, such as, let's say, in our Himalayan regions, you will see that the construction is of little different kind than what we see the modern construction, especially after the colonial period, and kind of influence that the British had on our construction in every sphere of life, and then building construction was no exceptions. So what you see is the masonry where we're using the brick, but the brick is embedded in the gridwork of timber. Okay, so one system in which you can see that you have a complete grid where a horizontal, vertical elements as well as diagonal elements, and then the brick is embedded, and of course the opening is created. And the other system is that you have a logs of timber which are arranged in horizontal fashion and sometimes in vertical. So what again they are trying to connect, these thick walls, and they go all around the perimeter of that structure. And definitely they have seen that there are advantages of such kind of constructions, especially in earthquake. And it can be a very artistic expression for your structure, so this is how they have been using it. And this is not only in India. If you go all around the world and you see the countries which is often visited by the earthquakes, they also have come up with the system, something like Hemis system in Turkey, in Portugal, you have a gaola, which is again can see this, the timber laced masonry, if can name it, and in France, and in England, Germany. I mean, many times, this is for earthquake and also some other kind of dynamic loads that can come from blast, can from mining. This is the store in Durham downtown, and Durham used to be a mining town in UK. And because of the mining blasts, the grounds used to shake, and then the structure had to be built to resist those shaking. And again, you can see this, the timber lace masonry. This building is just saved or kind of preserved, to show that that is how all the buildings were in this town, 300-400 years ago when this town was known for the mining. So, and there can be many variations, variations meaning is you're having using the dressed, undressed stone where you have expect more shear, but as you go up, there could be full brick wall, and then as you go further, you can see the amount of masonry is reducing. I mean, thickness is reducing, but the timber frame is increasing. You see that. So this could be just the half brick wall, and so that's how you can see the translations. And if you go really back, even the Greek and Roman culture, you will also see that they had the judicious use of the timber and the stone masonry. Okay, so and also the stone masonry and the brick masonry, so the layers of brick masonry. So as you can see that what is the central theme is that you have a stronger, more stiffer stone, and and interspersed with the softer, flexible brick. Same thing here, and you have the timber. So timber is good in tensile, and it also provides you the binding and bending strength compared to the somewhat weaker masonry. So people have been using these dissimilar materials to create the structure which is more resilient. So there are many ways you can explain that what this the timber is doing. First, you can think of them as like a shock absorber, because they're more softer material is more compressible compared to the surrounding stiffer material. Another is that they provide a slip plane where these units of masonry can move and slide along. So as they slide along, you can dissipate the energy through the friction. Okay, and also it adds to the flexibility of the system. But being connected, it provides you a kind of a tying action, not only in the vertical plane, but also in the horizontal plane. Okay, and maintain this overall configuration of your structure. And further, masonry is filled in small panels, reducing the span between supports. So you can see this, the effective slenderness, if I want to look at this segment, is very, very small compared to the one which is, if there is nothing present, then this will be your unsupported height. So that enhances its out of plane stability. And if that is so, then I can use very thin walls of masonry. Not necessarily it always has to be 1.5 or 2 brick thick. It could be as a half brick. And if it is confined and put in this grid work, it has sufficient out of plane strength. So the idea is that this grid work of timber of any other material can provide you sufficient out of plane, strength, and also in plane, and maintain the integrity of the wall so that it can continue to resist the vertical loads as it is undergoing the deformation due to the lateral loads. And in the performance wise, you can also see that their performance is much better than the so-called modern, the random rubble masonry or Asler masonry, and even you can see this, the very old and not so properly maintained building has done pretty well, and as you can expect, that this is not the combination of the random rubble and the Jidwari, where you expect the larger acceleration. The masonry has been quite intact, and there is similar performance mini structures. And I would like to take you to the building which is being constructed in 1932 for the Medical Research Center for a German group, and they wanted to have this research center built at Nagar, which is in near Simla in Himachal Pradesh, and they hired an architect from New York, and he visited this area, and he found that that the people traditionally have been building the timber frame laced masonry structures, and he wanted to use the and such structures have done well in 1905 Kangra earthquake, where the British built structures did not do as well. So all the reconstruction, even the British they did, was in this Dhajidwari construction. Okay, so he proposed that and built this complex in 1932. These are some images, and this structure stands still today after seeing many, not big earthquake, but definitely many small earthquake. And this is picture taken in 2009. And the first magazine of the center talks about the building that they had. And this is, I'm quoting from there. This method of construction is known here as Dhaji Diwar construction and has proved to be the best, if not even the only, method of construction that resists earthquakes, which used to quite frequent in this region. Most of the government buildings in Dharamshala, for instance, are built in this style and have proved to be the best. It is interesting that in its essential principle, this mode of building rather resembles the steel structures of modern skyscrapers. As you can see, coming out of an architect from New York, with the difference, of course, that wooden beams are used instead of steel girders. Thus, the wisdom of the people in its own way found the best solution, how to give at most binding strength and rigidity with the local material available. So the point is that, such structures have done well. Now, people talk about that, we can't use timber because timber is not available, and again leads to deforestation and things like that. And there are options, you can continue the same concept with the modern materials, such as in this case, we did some experiment in our lab where instead of timber, we have used this precast beams or the tie elements, So in this way, this interior grid is created by the precast. And then when we subject to the lateral loads, as we have shown in the my previous lecture, that they have sufficient, the deformation or rather deformability, going beyond. Masonry usually crack at 0.5%, and now you're going up to 2.5% or at least 2%, in the maintaining significant strength, you see. And you can play with, whether these members are continuous or they stop, only horizontal members continue, or you can have the diagonal members continuing. So you can play with this strength and stiffness and still can design, your wall. And And what we are doing is that at least you need the confinement from all around, and then internal confinement can add to your stiffness. If there's only horizontal, vertical, not continuing, there is a marginal, improvement in the stiffness. But the moment you put the diagonals, then you increase the stiffness significantly. So if you want this stiffness, then you can add the diagonals. And if you want only confinement and not so much the increase in stiffness, because increase in stiffness means increase in the decrease in the natural period. And if you remember the response spectrum, you tend to attract more forces. OK, so we need to have a suitable balance of stiffness, as that the forces are low and at the same time deflection are not large. And same thing we go with the strength. You see that. So this is the some experiments and some computer simulations. You see, you can see that the significant strength can have when we have the continuous diagonals and then just the simple horizontals. So, and we have some relations developed, then the people can use it. But one of the more concern in the masonry is because you see that the same wall is simultaneously being subjected to the in-plane load as well as the out-of-plane load, because earthquake has, has all the components, so even if we can resolve the components along the principal axes of the building, then you have both in-plane forces as well as the out-of-plane forces. And the member being very stiff in the in-plane, it gets damaged very quickly. So, and then it's being pushed by the out-of-plane forces. So it's very, very important that we need to know that what is this out-of-plane capacity while the wall has been damaged. OK, so typically we expect, that masonry cracks at 0.5%, but then we want to have this to be intact, something at 1 or 2% drift, you see. So this is what the nature is, that when it's uncracked, it has certain capacity, but that reduces as this in-plane damage continues, and then it reaches to some residual strength. OK, so we need to evaluate this, and to know whether this system is better than the other. So in a way, in experiments we can carry out, we can apply out-of-plane shaking. That's a more realistic simulation of your out-of-plane loads on that structure. So you can put this specimen on the shake table and shake it in out-of-plane directions. And for the in-plane, I can apply a known amount of damage. So I can apply 0.5% drift one cycle and create some damage and then run the out-of-plane tests, you see. So this is one way to utilize, two different testing scheme to evaluate out-of-plane resistance of the cracked masonry. Cracking is not antithetical to the masonry design, as in concrete, So idea is that you can tolerate certain amount damage as long as it is able to carry that vertical loads. OK, so that is the approach in designing our system. So I think I had played this video at that time as well, but this time I would like you to focus on the drift levels. So 0.5% drift level, that's we call damage state 1, and then we are applying the zone 5 level earthquake motions. OK, so what more important is, this is a replica of a half-scale model of your 5 meter here, 3 meters this way. So these 1.5 meter versus 2.5 meters, and the wall is 1 brick. So H/T ratio is close to 30, or between 25 and 30. OK, and now you could see that it got collapsed much earlier. But just providing two elements. So now you're dividing horizontally as well as vertically. Vertical is more important because now the unsupported height is only half of that, meaning is now H over T ratio has been reduced to half, something in range of 15. Okay. And if you recall from our previous presentations, this would do much better. 0.5% drift, and then you can see the damages. And we are all applying this L5. L5 means the zone 5 level out of plane shaking. And you can see that the loads are distributed. Here is the vertical path. These horizontals are not continuous. They stop. Only vertical is continuous. So this is much better performance by just changing the providing these internal elements, and you could go up to 1.75% drift. And masonry is damaged in plane. It's dissipating a lot more energy. It can actually resist even much bigger earthquake while maintaining its vertical integrity. It still can carry the vertical load. And as I said, this is just we wanted to feel it. We're applying some sinusoidal load. And you could see that the hysteretic behavior, of course, is pinched and somewhat, but what is more important is it's a load carrying capacity. You see that it still maintains the load. So that is and this is showing you the outer plane acceleration. So of course, it is held at top and bottom by the floors, and you can expect the maximum acceleration somewhere here at the mid height. So we had the accelerometers, and we can measure the responses. Okay. Now, so much so for that. So what is the traditional knowledge we are using in the modern context? So we are familiar. We know how to build the unreinforced masonry, load bearing type, and we also know that how we make the reinforced concrete frames. And then we use this brick masonry as a partitions, and we consider them as a non-structural element. However, during the earthquake, they are more structural, and sometimes they have detrimental effect on our reinforced concrete frames, because reinforced concrete frame, cannot work in the presence of the masonry there. So there is interactions, etc. Just saying that I'm ignoring in my analysis does not mean that they are, they will not participate, during the earthquake loads. So looking from our past experience, what we can think of is that we can use these columns as a confining elements for our masonry. And how can we do that? We have to just change our construction sequence. So first we have to raise this masonry, and then pour concrete for the columns. So what we do is we have, confining this masonry here with the boundary elements, and which are in confined terminology, masonry terminology, we call them as a tie column and tie beam, because they don't need to be as strong, as bigger, thicker as in reinforced concrete frame, because they can take the gravity loads as well. So it's not that the gravity loads are taken by the beam only; it's taken by the masonry here, okay, as in the load-bearing construction. So it has shown that it performs much better in earthquakes, and it is good for low-rise buildings. So if you have a 5-story, in fact, the recent Mexico code does not put any height restrictions. You can build as tall as you want, as long as the bricks have the sufficient strength to take this vertical load. So what we have is the plinth, and then you have the masonry is raised. Only important thing is about that interface. There is some toothing so that the concrete actually flows into this, and somehow connects with the masonry measure. And the openings we have, you have to locate these tie columns such that the opening is strengthened from sides as well as from these bands we run, so that it is strengthened all around. Okay, so we have a tie columns and we have tie beams here, and these can be referred as your lintel band and sill band. So the construction is very similar, and as I said the other day that in Latin America it is practiced, in Chile, and many other countries. This is the way the most of the modern constructions are done, especially for the residential purposes. So you can see that this is here. There are no tie sill band or something, but they make sure that the opening is finished with the floor beams, and so only in one end, and always the tie columns run around the openings. And the similar thing system is adapted in IT Gandhinagar for construction, though you can see the difference here is a fly ash brick. So you can use the clay bricks, you can use the fly ash bricks as long as you have sufficient compressive strength. Okay, something that what you need. Here you can see that the 4-story constructions using this fly ash bricks. So if you see the resistance mechanism, is that you have a load bearing wall, so no problem for vertical loads. For horizontal loads, still this side you can see that it goes into tension, this compression. This is more like a shear wall actions where the boundary elements are resisting significant amount of shear by the overturning. Overturning is resisted by this tie members, and shear is resisted by this masonry. And this can only happen if this interface is able to transfer the stresses. Okay, so that is where the toothing, etc., plays a role. So that we need to be able to make sure that this does not separate. And in contrast, what happens in your regular infill frames? When you apply this, is frame is deforming, and therefore the load transfer takes place through the diagonal action where the masonry is in contact, and very complicated transmission of forces. You do not know whether it is one truss or this is a truss of what width, and that depends upon the contact. Contact depends upon the beam and column, the flexural stiffness, and then masonry. So it's quite complicated. In this case, it's pretty simple. You can think of it as just a shear wall. Okay, and it registers the loads in shear. And of course, there is some moments, that also you can design as a short shear walls. So what are the benefits in that sense? First, it provides you the box type action of your all horizontal elements. They are all connected, so you have a better transfer of forces in various elements of your building system, and you have a greater in-plane resistance. Okay, because the tie columns also helps you, and then it provides you out of plane stability. So you cannot have even under the crack conditions, you have better out of plane resistance, and then greater strength, greater ductility, and greater energy dissipation potential compared to the URM load bearing masonry walls. So the reference, the system is somewhere lies between your reinforced concrete and the URM load bearing, but performance wise, it's much better than your unreinforced masonry load bearing systems. And we did some tests to show that how much toothing is essential. Should it happen every course or every 2 course? And what is the role of the toothing? Because certain codes allow you that toothing is not essential, but the tie columns have to be cast after the masonry is raised. So that basic principle of confined masonry is not compromised. But the role of toothing is something which some researchers or some codes, uh, have been kind of underplaying. So we wanted to see that, how does the in place. So I think again, I'm showing you the similar videos which I had done last time to gain refresh, the traditional English. That's all. So because here the vertical or frame elements are done first, and then you can see that very early using the connections, and it can very quickly. So after some drift, that's and and the school call is more than out of the significant for the masonry. Survives percent, I think, is we have done pretty well. 2% and still able to carry the vertical load. So you can see that the through the cable we are applying the vertical load. Um, so this is the case, and then you can also see that what happens if you create an opening. This is a traditional construction where you infill, and then of course there is a lintel band, not continuous. And as we have seen the last time also, this is the plane where frame has the weakest shear capacity. So you'd expect that these piers will be subjected to most of the damage that is observed. And you can see that these piers are such proportion that they are rocking inside. So you can see the pushing of the toe here, and on the other side, and during the out of plane actions, this looseness and we can fall up. And you can see the masonry here, they're not being stressed because this is not how the load path is. They are pretty much not participating in load. So you can see that the chunks have come out, and this is in bad shape. But its counterpart, when we have the fill band, and we have a lintel band, elements, and then the something which is encloses the openings. So now you can see the sphere, which is critical, is now actually confined. Okay, so and you can see that the damage levels is much smaller. And now the other the spandrel masonry here, sorry, sill masonry here, they're also participating in load sharing. Also the spandrel masonry. So you can see that this is in our modern concrete and brick masonry. We can create a system to for better earthquake resistance. And another important thing to note is the aspect ratio, or rather the distortion of these openings. That's also is very limited. So tendency, likelihood that these doors will open after the earthquake. So here we can see that we are applying 2 times, 3 times of the zone 5 ground motion in vertical plane, and it is almost intact. So this is just showing you the crack map of the structure at the end of the test. And this is your infill masonry. You can see all the interfaces, and when it's opening, then you can see that the damages that we saw in the in the piers. Okay, and once you have the confined masonry, you can see that this is working all around, and you can expect that this whole thing is like a shear wall system with the toe crushing at either ends. Okay, and then you have openings. Then this is, of course, is the area where the slender piers are being worked upon. And in this case, if you notice that the horizontal bands are not continuous, you see. So this is something what they do in Latin America. They do not keep this band continuous. So they take the tie columns from floor to floor, but they do not take this continuous. What we did in our study is that we need to keep this continuous, and tie columns don't have to be continuous, but of course they must run around so that they stiffen this opening. Okay, so this is what the system difference is, and now you can see that this performs much better than this. Okay, so we know that this horizontal bands are necessary, and just only thing that we have to do is to construct them in such a way that the masonry is done first, and then these tie elements are cast later. Okay, and same thing where this is again the Latin American practice in which you can see that. So openings are large, this is large slender masonry, but had this been continuous, probably the deformations would be much smaller. I did not show you the videos of these tests. Okay. But you can look at the behavior, hysteretic behavior. The area under these loops tells you that how much energy was dissipated per unit volume. And the important thing to note is that confined walls actually dissipate more energy. They get you more strength, peak strength, and more healthier hysteretic response as compared to your infill walls. And even with the openings, you see that this is the conventional infill with the lintels. You can see the strength levels. But if it's well confined and all around, you get to 96.7, 91.5. This is same as for the solid walls. If you see here, this is the solid wall. So what it means is that even with the presence of this opening, if they're well confined as in our system, we do not lose any peak strength, despite having an opening. And and this continuous horizontal bands are better than the vertical tie columns. Okay, so this is another comparisons. Pretty much now you can see the drift levels, which one is dropping, and I'd like you to focus on this infill masonry, which is this blue line here, and the confined masonry with the 2 openings for windows, which is this the dotted black line, you see. So it reaches the same strength, much strength, and this is deformability what matters. And of course it is stiffness is much less because you have the openings, so that causes the decrease in stiffness. And that you can also see with the solid wall confined masonry, which is red line. So this has a smaller stiffness, but not very different. So these are some quantification of the results, and that helps you in developing the design and the manuals, codes. And I will now talk about some of the manuals which we have brought out from National Information Center of Earthquake Engineering, which I hope most of you are aware of. And this was the first a kind of manual by Dr. Brizev, and then there's Hindi translation. And then recently, with all these developments, we have revised it and given you more input from the architectural point of view by Dr. K. Mitra. We also have a guidebook for technician and artisan prepared by the Swiss architect, and it gives you step-by-step guide for construction and something like this kind of sketches. Okay, now in the NBC in 2016, there is a chapter in Axial referring to clause 8.9 about the confined masonry building construction. So it actually introduces the construction type, but does not give you much details. It's more prescriptive and something for the 1 or 2 story buildings. Now we have brought out a code which is under discussion with CD 39, and we submitted long time ago, but the way the BIS works, it takes much longer for the code to come in final form and the published form. So I will try to show you some of the important part of this code, and where you can engineer your confined masonry, not just the prescriptive. So it talks about that you can use any kind of masonry unit. You can use the burnt clay, even the fly ash bricks, as I showed you, or even ACC, but you need to have a sufficient strength. You see, that is coming from your calculations. Something at least for 2-story building, you should have 3.5 MPa. More than 2-story building, you need 7 MPa, and concrete blocks should be more than 7 MPa. So something like, if you're using AAC, make sure that it is 3.5 or 4 MPa. About the mortar, it's better to use the cement, lime, sand mortar, lime mortar. So this is not very expensive, and but medium mortar M1, 1 part cement, 1 part lime, and 6 parts sand. It gives you the strength of about 3 MPa. What you need is good workability, and adding the lime does that. And somehow use of the cement sand mortar is not good, and this is kind of again a deviant behavior propagated by our building codes. So concrete should be at least M15 for your tie columns and tie beams, and reinforcement you can have Fe415 minimum, but you can use higher grade if it's not available. Mild steel can be used for the stirrups. Building configuration, as in any seismic design, we say wall it should be very simple, regular shape, length to width ratio should be less than 4, so it's not too narrow. Configuration, walls should be symmetrically placed. Okay, so these are some guidelines that you need to have the minimum amount of walls, considering the vertical, some of these offsets are not good. Very similar to your IS 4326, is just reminding you here as well. Now, if you see that the plans, this is not good. Reason is that this arrangement has more walls for earthquake in, let's say, north-south direction, but in the east-west direction, you have very few walls. So this is not good. So you can arrange it something like this, that there should be walls in both directions. Same way in this, and these are the things which architects should be done at the planning stage, that you should have sufficient number of walls in both directions. No offsetting or discontinuous walls. So this is also not very good for confined masonry, and an arbitrary placement of openings, makes it harder to place your vertical tie elements, and even if the vertical, then you may not run your band. So there are some restrictions on that. As I said that, slenderness, should be less than 25. So the H/T should be maintained. So if you're going more height, then of course you have to use a thicker wall. And this is the location of this is from the Mexican code, So here you can see that they do not have the prescription of the horizontal band. So this they find is easier to construct rather than putting sill band, and now you can see the lintel band and roof tie element is combined. So that way you reduce one. The tie beam spacing should not be more than 3 meters, and the column is 4 meters, because then the effectiveness of this it reduces. So you need to have a tie column spacing, not more than 1.5 h. H is the story height. So these are some rules based on the configurations, something that works. And the tie column and tie width dimension is actually 6 inches or 150 mm times the thickness of the wall. And this is another plan showing you that where you should place your tie columns and the wall. Okay, so the minimum thickness is 110 mm. H/T ratio should not be more than 25. Unsupported wall height should not be more than 2.5. So height to width ratio of wall should be kept less than 2 for better lateral load transfer. So if this wall becomes narrow, if you can go here, if this is very narrow, then this is not very effective. So the idea is that you need to keep this tie column so that they're shear controlled. Now this wall here now is more flexural controlled, so which is not a better way of utilizing the material. And then the parapets should be limited to 1.2 meters. Then comes the openings, small openings are better. So the way we define is that if opening is more than 10% of the wall area, then it's large. Less than 10 is the small, that's the 1 thumb. And this is what we're talking about, that you can arrange your elements as not having the continuous horizontal elements. But as I said, this experiment is showing better. So you choose this option. But even option A is good. And then large openings. So if you have large openings and not strengthened all around, then you'll not use, this wall is not resisting any earthquake load. So this cannot be used in calculations. You can make this, but this will be not considered to register earthquake load, or this does not qualify to register earthquake loads. But if it is confined by these vertical elements, then you can. So you can take this area is resisting earthquake and this portion is resisting. So horizontal shear is resisted by this masonry and the masonry here. Similarly, if it is more than 0.25, then you have to confine it like this. So these are some guidelines, and again the diagonal actions, because of shear, you have predominant. So we don't want that the opening should be obstructing these diagonals. So if they're outside and small, we can they do not affect the shear resistance as much, but if they are, then we have to make suitable adjustments. The other question comes is that how much wall is needed? Okay, that should be there to register earthquake loads. So there is a term that is used as wall density or wall index. So that tells us that the total earthquake resistance of your masonry building. and some kind of initial assessment that how much wall area is required. So it can be defined per floor wall index as area of the wall divided by area of the floor plan. Okay, so this is will be expressed as in percentage. So let's say this is the building plan that you have, and let's say we are considering the horizontal load in horizontal directions. Then you know this wall may qualify. Maybe these walls there are no confining elements at the end of these walls. Okay, this is the opening, so this wall doesn't qualify to take the earthquake level, but this one does. You know, this one does. This one does here. You know, this one is qualifying. This one is qualifying, but this one does not. This is a small portion. Okay, this one does here. So this is one which is shown in yellow actually qualifies to take the earthquake load in the horizontal directions or x directions. Okay, and when the earthquake is in other principal direction, let's say in the north-south y-axis, then these walls can be considered as the one which is resisting the earthquake. So they should be symmetrically placed by and large, and should have the same total wall area now divided by the plan area is the wall index. Okay, so this is how we calculate this wall index, and this wall index of a floor multiplied by number of floor will give you the total wall index that is required. Okay, so typically that could be in seismic zone 5 is 2.4. Okay, wall index per floor, and then it reduces as the PGA reduces. Okay, and this is based on a limit state design method that we'll talk about in a few minutes. And we're assuming the compressive strength of the unit, that's a brick or whatever, 5 MPa, and mortar is type M1, and average floor weight is 12 kilopascal. So this is just for preliminary sizing, for simple buildings, these are the numbers, but you can calculate it by looking at what is the total, horizontal floor force that you may have for your building. So you know which zone you're located, the time period of the structure, you can calculate SA by G, you can calculate the AH from IS 1893, and then this horizontal seismic coefficient multiplied by the weight of that floor gives you the total force. And then we take this load factor of 1.5 divide by the masonry shear strength divided by the partial safety factor. So this will give us the total wall index for that floor. So that's a simple calculations, and which is good enough for the low-rise buildings, and of course it can be extended to buildings of any height as long as you have the masonry which can provide. And there are many other suggestions that for simple buildings, the height should not be more than 6 meters and things like that. So meaning that for two-story building, we're considering simple. So we can design just based on this wall density and not worry about the dynamics and other stuff. But we can design this as we do for the reinforced concrete, or we can follow the same limit state approach. Design loads will be over characteristic load multiplied by the partial load safety factors. We can have the load combinations, and then we can have the design strength of materials, which are characteristic strength of material divided by the gamma m. And gamma m is for masonry is typically taken as 2. That is what is proposed in the code. Because there are more uncertainties, more variations in material properties of masonry, we use a larger factor. So the axial load resistance, you can think of that, area of masonry multiplied by the prism strength of masonry, and and then we have 0.4 here. So which is you can think of as the reduction factor, same thing as what we have 0.45 for the concrete and FCK, 0.75 for the steel. And then you have this KS, which is the slenderness effect, or rather stress reduction factor for slenderness of the wall. So that's how you calculate the axial load resistance. So contribution of masonry, contribution of concrete, and contribution of steel. So what you're saying is that this is where this portion is the concrete and steel, this portion is masonry. So I can calculate what is the vertical load this wall is taking by using the relations. Now, if the moment is present because of the lateral load, then now you have the interaction of axial force and bending moment. Okay, so now in same thing in the concrete, you have the PM interaction curve. So this is the idealized interaction curve for this wall where we have a tie columns, and these are the equations. If it is less than 1/3 PU, then this follows the straight line, and so this is the equations, and your derivations you can see in the commentary of the code. And so that's how you look at the PM interactions. And for the shear, it's quite complex. You have the diagonal strut model, that is what we are using to develop these equations. So what happens is that some shear is just taken by the masonry and some by the tie columns. Okay, so that if you look at the displacement versus the story shear, at point A represents that the masonry is contributing. Okay, so all the shear is taken by the masonry. After it cracks, then the load transfer takes place to the frame now, or the tie column participating more. So A to B, of course, there is a reduction in stiffness because of the cracking in masonry, and the load gets transferred to the tie column. And this is the from B to C. So we can see that this gray area is your tie column contribution, and this red is somewhat is your masonry contributions. At any instant, both tie column and masonry is contributing and resisting the shear. So it's quite complicated in that sense. But then we have had the Coulomb shear kind of criteria, So this is that simple Coulomb shear. So you have this friction factor multiplied by PD, will give you the shear strength. And this is your VM into area. That's a bed joint sliding. So this is that, and then this is the friction factor time axial load. So, and then there is a reduction factor 0.8. And this F is aspect ratio. Okay, so if it is very slender H over L, then F is 1, but if it is squared, then it is 1.55. These numbers come from experimental, curve fitting, to the data that we had. And the VM is masonry shear strength, which is related to the compressive strength of brick prism. So you take 5 brick prism, 5 brick stacked and with the mortar and test under compressive load. So that gives you FM, and this is 0.18 root FM, very similar to what we do in case of concrete. All the shear properties, etc., have square root terms of your compressive strength. So, and then there is a minimum amount of longitudinal reinforcement, same as in the for reinforced concrete 0.8%, and people even talk about that this can be reduced. Let's see. And then there is a minimum transverse reinforcement. Okay, so very similar to your RC construction. Okay, now the major project that we have executed in India is on the Gandhinagar campus, where the hostel buildings was a 4-story and 3-story staff and faculty quarters are built in the confined masonry. Okay, so they use the fly ash gypsum brick, not the clay brick, because they had to use this fly ash as they are close to the power plant, but in the foundation they've used the clay bricks. So that you can set up a plant there, but you have to make sure that is 4 stories, so you have to have at least 7 MPa strength. So they went for the again cement lime sand of type M1, which is 116, concrete M25. Okay, Fe 500 for TM reinforcement, 8 mm size for the ties, and 10, 12, and 16 for the vertical reinforcement. Okay, these are similar to your RC constructions, so you can see that they have the spread footing, and then they have a plinth band over which this the masonry brickwork. So this is the clay brick all over, and this is simple. So you have the plinth band all around, and as you can see that the tie columns are rising from the plinth band. So that's simple, but you can raise it from the foundation too. You know, either way is fine. So that's some sketches for the plinth band, and this is the construction of the plinth band, and then you can see this reinforcement of the tie columns. The bricks are soaked before construction. These are some pictures at the construction, and then of course you have to create a toothing, you know, so you have to make some gap, and this should be at least 5 centimeters. I mean, it's typically that so that your header joints are broken, you know, they don't align. Okay, and you don't want too much, because if it's too much, then if you're pouring the concrete, it cannot go inside. So just enough so that the concrete can flow and fill this cavity. This is what the at the corners, and then this is, and the more pictures. So usually you go 1.5 meter wall height, and then you cast the tie columns and continue, wait for 3-4 days, and then continue. So that is how the construction looks like at various stages. And then the lintel bands, we just talked about, you know, what their role is. And as you can see, this is now the preparation for the lintel bands. They're done at the height. So you can see here the lintel bands. And way the construction was that there is a very small masonry, you know, between the lintel and the roof. So of course you can play with that, you know, and if your openings go all the way up here, then you can eliminate the lintel band. And same risk, you know, use for the reinforce. You have to make sure this 90-degree hooks, 135-degree hooks all around, and use the deformed rebars. Same constructions, and these are some details, you know, that you can put the spatial confinement over SO2, where you can reduce the tie spacing. As you may have seen that, you know, this works like a shear wall, so there is kind of a plastic hinging or toe pressing. So if you confine the, you know, this area to be a 2T or a 1/6 of H0, then you get a little better performance, at least control the disintegration of concrete and masonry around it. So these are some details of lapping and what is more cumbersome is sometimes is putting this formwork around it, you know, so you have to be little innovative and creative, you know, in putting this in place, because when you pour the concrete, there is so much of lateral pressure, and make sure that there are some arrangements. Here is the need to take this anchorage of the longitude. So at the T connections, you have to install this angle and this so that they are connected, you know, because you're transferring the moments, you know. So some kind of details are needed. I mean, this is another picture showing you that how you have to connect it. If you cannot take all the way down, you can have these red bars installed on the inside. And this is not good, you see, because it should go to the exterior and the outer face. And of course, you cannot just end it like this. So basically, you have to make it so that you can be able to transfer some moments. The same thing at the anchorages of the longitudinal bars at the corners. The lapping, you have to provide 40 times because all these are tie members, meaning is they're carrying the tensile forces. So at least 40 times of the diameter. This is another way of installing where you can pour the entire height in one go, but it is better to do it in steps. So shuttering, there are many props you have to use to keep this in place. This gets actually tedious if you do not have room on the other side. So that's where you have to be a little bit more creative. In this case, you can see that the tying wires are being used to hold this formwork in place. And if you don't do this, then the concrete may flow out, and we have a little bulging, you know. Just like that. So there are many. These guidelines show you some examples that what to do, what not to do. The formwork can be nailed to the walls on both sides. And then, of course, you go to pour the concrete on the roof to create the floor slabs. Another thing is what is the cost is, you know, so the structural cost is typically for this IT Gandhinagar project was 8,600 per square meter. For the faculty hostel is 8,900. But then if you consider academic buildings, which is RC frame with masonry infill, is 15,000. So there is saving, you know, from in terms of using the confined masonry. Okay, so that's the one data that we have, which shows that you can have significant saving using this confined masonry. And this is how these buildings look after the construction, after they're finished. So there are more information worldwide. You can go to the ERI website, Confined Masonry Network, you can get more information. And I can conclude my talk by saying that, of course, this earthquake resistance is not something new. People have been trying, and one way was to use for masonry work, to use the grid work of the timber or any material which is good in tension to provide a strength and a stiffness to the system. And this modern confined masonry, as I talked about, can help you do that, and can be used for our modern, especially for the residential buildings where the floor or the span is not too large, so that's, and again, height is no restriction if you have the good quality bricks. So with that, I conclude, and I'll stay if you have any questions or comments on talk. Thank you.
Thank you, sir, for another insightful and eye-opening session. It was a great session as it included right from ancient masonry to traditional masonry, and finally in depth about modern confined masonry. On behalf of the Applied Mechanics Department, I would like to thank you, sir, for sparing and sharing your time and knowledge with us. Sir, it would be great if you could share this presentation with us. By doing that, all the participants could be helped. Sir.
Okay, we'll do that.
Okay, our email ID is head_applied@ldce.ac.in. So with your permission, Durgesh sir, we may open this session for questions.
Sure, please.
Okay, so those who want to ask questions may raise their hands, please. Ma'am, you are unmuted, so you may ask.
Am I audible now? I guess I am.
Yes, you are.
Yeah, good evening, sir. So my question to you is like two things which are confusing me, as in you had mentioned that the compressive strength of the brick, of the mortar should be less than that of brick, right?
Well, that is normally that's the way it is. You know, the compressive strength of the mortar would be less than that of brick.
Uh, Correct. So does the generally when we are working with machinery, sir, so the question is like, everything bogs down on like whether the mortar is stiff or the brick is stiff. So generally in Indian conditions, when we see that the mortar is more stiffer than the bricks. So what I mean to say, sir, does the modulus of elasticity of brick or mortar comes into play when you are dealing with confinement of machinery?
No, it's not. I mean, it's the same masonry. See, it changes a little bit, but it's not. I mean, like if you're a north, definitely the brick will have, you know, is more stiff and stronger compared to the mortar. Even if you're in south, you see, uh, I still believe that you should be using the brick, which has a compressive strength of at least 3.5 MPa. You see that, so 3-4 MPa. Now, even if 116 mortar has a design compressive strength of 3 MPa, so that is also lower than the brick that you will be using. Now, coming back to the stiffness, that could be some issue, but that doesn't change very much the behavior. Okay, so I do not see that, you know, the masonry. If you can use it for load bearing masonry, you can use it for confined masonry. There's absolutely no difference. Okay.
Okay, and so then the second thing is like, is the confined machinery successful with the double blocks also? Because nowadays, sir, since this is giving a very strong competition to the conventional bricks, so how far it is performing?
No, which brick? I could not get that.
That the autoclave aerated concrete blocks,
Okay.
sir, the
Yeah.
ones
So
which yeah.
the AAC blocks, you know, the only problem is that our we've done some experiments, you know, in our lab, and the problem is that they do not give you the AC block of sufficient strength. You see, because of the code requirements, they always say that it is 3.5 MPa. But if you test it, they would, you know, will be in the range of 2.5 into MPa. So I would rather, you know, be cautious while for using them as a load bearing. Okay, for partition they are okay, you know, for which they're being used. In fact, it is good if they have a low strength, okay, because then they do not interfere with the frame actions. And we have one paper showing that if a AC blocks of a weaker strength, they also reduce the adverse impact of the open ground story. So that is good for your multi-story infill constructions, but unless they have a sufficient distance, at least 3-4 MPas, something which is required to take this vertical loads, they may not be good for the confined masonry construction.
Okay. So I'll tell you my, what was the basis for asking this is because so should I believe that somebody who is working, let's say in an area of research where somebody is coming with alternative brick unit, okay? Let's say a straight competition to fly ash brick or a red brick. So should the person can be positive that at least as far as the wherever the areas where the confined machineries will be coming up, especially in the seismic prone areas, and if we look at the rural areas where again we try to give them a more stable housing facility. So any bricks which is, let's say, having a strength of more than 9 megapascal is applicable to be used for confined machinery.
So 9 megapascal is, will be needed only we want to go for 2-story and above. So 6, 7, 5 MPa is also good enough, but I would say 7 MPa. So 7 MPa is good enough for any construction, but again, as I said, that you have to also see that how much vertical load that is coming with the earthquake load combined, and so that best way to represent is not just the unit strength, but rather the prism strength. And prism
Correct.
strength is because you're not only putting the brick under compression, you're putting the brick under compression along with the mortar. Okay,
Mhm.
so the prism strength should be sufficient, at least 4-5 MPa. I would say 4-5 MPa. Okay, so then you will have a sufficient tensile strength, sufficient, shear strength, etc. So you have to look at both. And I mean, one cannot use this AC blocks with a 2.5 MPa for load bearing. That's the uh, you know.
Right. So if you have a brick unit, let's say, which is having a 28-day strength of 18 megapascal, 1/8, right, sir?
Uh-huh.
So then can we aspire to go for 6-story, 7-story buildings in
Yes,
confined?
that's right. Yes, but you have to do
Okay.
calculation. Yes, you can. Yeah.
Right. And so how about how influential is this bond when it comes to confined machinery? I mean, I saw in one of your slides that bonds also ought to be good. So do they have a big bearing in this thing apart from the compressive strength?
Yes, because unless there's the kind of the concrete, the tie column is not well integrated with the masonry, then you do not get the what called the boundary effect. You see that to have this boundary effect, proper transfer of shear at the interface, the two things should be there and it should be properly filled up. And that can only happen if this concrete is of the your tie columns and tie beams are cast after this masonry is laid. So that's quite important.
Okay, sir. So when you're saying bond, you're actually talking about those boundary elements in the masonry. So what I thought was, sir, when you're talking about bond is like when you're connecting two brick units, masonry units with the mortar. So how they are performing the brick to brick, how is it performing at interface?
Well, that is also important. That is same as the good rules for your masonry. The good rules for the load bearing masonry is that bond should be good. And that bond can only be good if you use the lime cement mortar. Okay, lime is important. Without lime, you cannot have a good bond. So if you think about any international standards for the mortar, let's say ASTM standards, you do not find any mortar which has no lime. Okay, they have type M, type S, type N, type O, and all of them have limes. You cannot think of a mortar without lime. Only in India, we do only cement sand mortar.
Right.
And that cement sand mortar is very, very stiff. And now with this, the early day gain in the cement, they set very quickly. And if you see the process, the way the masons actually lay the brick, they keep tapping, they keep moving the bricks, if their alignment is not right. So basically, whatever the bond that develops in first few hours actually get broken. So you basically have no bond. So you need to have something which is slowly setting, slowly hardening, and that can only happen with the presence of lime. Okay, so lime is quite essential um, in that. So that bond is important, because that bond is important to provide you uh, protection against the moisture in grass and many other things, and even the flexural strength. So
Correct, correct. Thank you very much, sir. Thank you very much.
If anyone else has any question, then they may raise their hand.
Sir, I want to ask that hostel building of IIT Gandhinagar is constructed as a load-bearing structure. And the second question is, what is the main reason for cost saving in confined masonry for this case study, sir?
of course you have to consider this load. Now we've given all the equations, so you are analyzing for provide enough shear strength. Your load is carried by the masonry walls. So masonry walls should carry the vertical load that is coming out from them. So in that sense, it's a load bearing. And when there is a lateral load, then they have to be analyzed as I showed you for the uh, axial force and moment interactions. Okay. So and what was your other question?
Sir, what was the main reason of cost saving? Because of the steel savings in our ductile detailing?
Of course, that's the one thing, because here if you see this, all columns are only 230 mm, the width. Otherwise, if you have the 4-story and then you distribute all that load, those columns would be heavier. There will be more steel. There will be more, confinement steel and things like that. You see.
Okay, sir. Okay, thank you.
And then the construction cost, also the formwork, if you see here, is basically it's supported by the wall. Okay. Otherwise, in other cases, you have to provide so much of the formwork to support the beam and the slab, because they're cast together. Okay. Here the slabs can rest on the wall, which you've already built. So again, there is a saving on that. So and the saving on the so this is the source of the major saving. And I would say that for the academic area, there are long span. Okay, so there may not be very good direct comparison. Okay, but definitely the cost of this confined masonry construction is not more than the load bearing masonry. In fact, that is better comparison rather than being comparing with the reinforced concrete buildings. Okay.
Any other questions?
Sir, during construction of wall, care may be taken that the slender wall may constructed on slab, and while we are क्या बोलते हैं उसे, हम जब वॉल बना देते हैं, बाद में उसके आजू बाजू फॉर्मवर्क लगाने के लिए किसी ने धक्का मारा तो वो वॉल गिर तो नहीं जाएगा ना सर? Because walls are having very small length and slender, they are also slender.
लोड बेयरिंग कंस्ट्रक्शन में आप उन्हीं वॉल के ऊपर ही तो छत डालते हैं, तब तो नहीं गिरती।
यस।
हाँ, तो आपकी जो ऐसा कोई आशंका नहीं है, थोड़ी सावधानी की तो जरूरत है, इसलिए कम से कम आप 4 या 10 दिन आपको थोड़ा सा इंतजार करना पड़ेगा, सो दैट की दीवार थोड़ी मजबूत हो।
ओके सर, ओके, डन।
I think there are no more questions, sir.
Okay, so thank you very much, and thank all your participants and you especially for the.
Thank you, sir. Thank you, sir. Wonderful session.
Thank you, sir.
Thank you, Chaitanya.
Yes, sir. It was a really wonderful lecture, sir. Please. Thank you. Thank you.
So
Okay.
here comes an end.
Sir,